MPC. Okay, so this talk is about the most recent developments in nonlinear and robust MPC algorithms in my team. And this is joint work with Jonathan Frey and Florian Messerer and the other co-authors of the papers that I will cite. So the talk has three parts. The first one is, as I promised, a little bit of real-time sequential convex programming to just get the main idea of the algorithms behind in the language of this course to everyone. In the second part, I want to make a few remarks about the software packages BLASFEO and ACADOS. BLASFEO is actually a linear algebra package, which is independent of optimization, but it's tailored for embedded optimization applications, basically MPC. So it's really, well, up to a factor of 10 times faster than other similar packages for the same purpose. And ACADOS is based on BLASFEO and is actually a real-time iteration method that basically implements the method that I explained in the first part. And the third part of the talk will focus on a part of robust MPC. And I mentioned already that MPC is actually by its essence, it's a deterministic system optimization, right? Because in MPC, we want to solve finite horizon problems by basically derivative-based methods. And this can only be done fast if we have a, so to say, one plan. And in deterministic dynamic programming, we know that one trajectory, so to say, is the optimal solution to the problem. Once we have stochastic or robust systems, things get much more involved. And basically, the problems would grow very quickly, very big. And in order to avoid it, some people use tubes, as we will do here. That's basically predicting like uncertainty intervals around trajectories by linearization. And that makes problems still big, but you can treat them a bit easier. And one of these interesting algorithms I will present, that's based on Florian Messerer's PhD work. So the starting point is real-time sequential convex programming. And so let us recall what nonlinear MPC does. It solves parametric nonlinear programs. Yeah? Sometimes you put a little p in front of the NLP to express the fact that it's depending on a parameter. So let's look at the problem again in the language of this class. We have the cost, we have the end cost, we have the initial value constraint, and here we have an index SI bar, which expresses that this state will actually change during the execution of all our optimization, right, of the MPC controller. And then we have these inequality and terminal constraints, path and terminal constraints. We can summarize all variables, the trajectory S and the actions A in a vector that I will call X, now on the right side. And one interesting thing is, which is pretty often true in applications, is that nearly everything is convex in this problem. C, E, H, and R are all convex functions. Yeah? That's very often by design. And in the few cases where you want something non-convex there, you could do little tricks in order to get back to the algorithms I explained now. But it gets so much simpler to explain when I assume this convexity. And typically think of C and E being quadratic and the constraints being linear functions, affine functions, okay? So then I don't need to change them because they are, so to say, already convex and beautiful. And then what does SCP? Oh no, sorry, let me first summarize the problem. So now I zoom a bit out and now my nonlinear program is here on the right. It's a problem which still has a convex objective F and convex constraints H. Okay, I switched the sign, so this should be smaller than 0, so that convexity implies convex constraints. Yeah, H smaller than 0, and then H should be convex functions. And then crucially, we have these equality constraints, which summarize all our system dynamics. I call it big G of X and SI bar. And SI bar is the parameter that changes, and it's entering our constraints linearly, which makes things very nice and beautiful. This was too much. So at the bottom, the MPC policy just solves such a problem to optimality in the perfect case. That's what we call ideal MPC. Takes the solution of this problem for fixed initial value SI bar, takes the first control action of that A0 and calls this the feedback control law. Yeah? think this was made clear, hopefully, in the lectures on previously. So we have this finite time horizon, and then we optimize and we just take the first control. And the closed loop system would then be given by basically our system, if it's acting like, if our model and the reality do not have model plan mismatch, there would be no disturbance epsilon. And in typical applications, we will have, of course, disturbances, which we are not able to model well. Otherwise, we would have them in our model. So this Si plus 1 bar, this state will typically not be the one that we predicted, right? It will be something else. So we need to react to that, and we want to react to this fast. Yeah? And now the question is, what algorithm could you use like at the core to solve this? And we already explained the SCP algorithm. So sequential convex programming just takes this high level. Let's take the high level perspective first. So let's look at the right. We have a non-convex problem only because G was nonlinear. So we linearize G at the point where we are, which I call xj. Yeah? J is another iteration index. It's actually the iteration of the optimizer inside each problem, right? Si bar I keep fixed, that's the problem. And xi is now iterating, and I compute the next iterate, xj plus 1, by solving this convex problem, which I just got from a linearization. And this linearization along a trajectory we do with a fully simultaneous approach. That's what we advocate, right? So it could be an infeasible trajectory. It's just linearizing the system as it was on the left side. Actually, I can show this. The linearized system looks as simple as this in this beautiful setting of convex constraints and cost. So you linearize just the system dynamics, and please keep in mind, it's now depending on the linearization point. Maybe now you get completely confused because we have 3 indices and they all refer to some form of time, right? So let's concentrate what these 3 indices mean. The highest level is the I. I enters here the Si bar, for example, right? So that's the index that tells us what's the optimization problem that we want to solve now. That's the real world system. Yeah? Then there is possibly an inner loop J, which is these updated trajectories, best guess for a trajectory starting at Si bar. And then these trajectories itself, of course, consist of multiple time steps, which we, by convention in this perspective, let's start them at 0, yeah? Even though physically, of course, they correspond to a time horizon in the future, right? But from the optimization perspective, they're just variables that always start at 0. It's the same number of variables. And so this index is called K. Yeah, so if you, please keep these 3 distinguished. Of course, now you might say, and this is actually exactly what we also said, so now we have these convex subproblems. We know that we can solve convex problems very fast, in particular if it's a QP, extremely fast QP solvers exist, so a few milli-microseconds sometimes, and you have a QP solved. In order to arrive there, very often you have to simulate your system. And simulation with multiple steps, you remember these Runge-Kutta methods, many steps, many stages, very long, possibly long nonlinear functions. So this F might be difficult to not only simulate, but also then to linearize. So you need to get all these Jacobian matrices. So now the question is, each SCP iteration does 2 things, right? It linearizes the system, and then it solves a convex subproblem. Linearize again, solves a convex subproblem. While you do this procedure, the real system might evolve, right? So you basically work on a very old problem while you try to solve it. You know your system, I mean, you have to decide on some actions in the meantime. And so the idea of what comes next is that we just say, if we have these powerful convex approximations of the real problem, which turn out to be quite accurate approximations of the truth already, why can't we use them directly as feedback law? So actually we sacrifice the idea of solving optimization problems exactly, and we do the following. We do what we call a real-time iteration. So you solve only one convex subproblem in each sampling time, and that means basically that you identify the index I and J. That's it, so to say. And you always take the very latest measurement Si, or Si plus 1. Okay, sorry, I changed notation in the slide, but not completely. So here you have, let's look at it's Si. So we have our problems index Si bar. We take the latest trajectory guess that we had, linearize at that point, solve one convex problem, and then take already the solution from this problem we call, it is the one with the index I, yeah. I mean, and that one we apply directly as feedback. So the assumption here is, of course, that we can solve these problems faster than the sampling time. So you would actually do the following computations, and that's what we do in the algorithms. You would first take whatever trajectory you guess you take it. Maybe you modify it a little bit. There are some tricks like advanced step real-time iteration and so on, or shifting or whatever. But anyway, so you have some guess that you think is a good linearization point for your problem. And in the most common case, we just take what we had in the optimizer without any modification. Yeah? So you take this last guess, you linearize there, you prepare the QP or the convex subproblem as much as possible, and only then you look what's the latest state estimate SI bar. And then you take this latest state estimate SI bar and you basically push it to your QP solver who is, so to say, ready and waits to solve this QP with all the data pre-processed. There's some procedures called condensing and so on. So at that moment that you have the S available, you solve the QP, and then very quickly you give back the controller here at the bottom. So in that sense, you minimize also the delay to an action. Yeah? So that's a crucial implementation feature. If you want to boil it down to two ideas, then one is that you only just do one iteration per problem. And the second one is that you divide the computations into those things that you can do without knowing SI bar. And then you solve for this given SI bar as quickly as you can in order to not only reduce the possible sampling time. Yeah, the sampling time is now basically as short as one SCP iteration. You can never sample faster than one SCP iteration with this algorithm, but the delay that you have until you give a feedback to a state estimate could be significantly shorter. Okay, I think here the index SI, okay, should always be, SI plus 1 should be SI. So this idea is implemented in the software packages that I mentioned, and I just want to start with the most basic, the foundation of everything in the solve community, let's say, on the side of solving is linear algebra, right? So solving is all leveraging the power of linear algebra, basically solving linear systems. A Newton type optimization needs linear algebra for all the matrix multiplications and the factorizations. And in embedded optimization, these matrices very often have fixed dimensions. So we know them, so to say, they are this size. And they consist very often of lots of dense blocks, like these structured linear algebra systems in a QP, for example. And so BLASFEO is tailored for that, tailored for embedded optimization. And the first thing it uses, so to say, intrinsically a pen and major format, at least in its most efficient version. And in contrast to standard BLAS, it doesn't do reformatting. I mean, standard BLAS takes a matrix, copies it, so to say, to a different memory format, which is then better able to use the processor. And afterwards, it's copied back. And this is copy-paste. Sorry, a copying operation is just order of n square, if n is the matrix dimension. So it's not so much compared to n cube, when you have a really large matrix, and that's what BLAS usually does. But in BLASFEO, we know that we have medium-sized matrices, maybe 10 by 10, or maybe 100 by 100. And in this context, it makes a difference to copy or not to copy. So we basically keep the format fixed. Yeah, so the matrix is stored in this format, which is a bit inconvenient at some other points, but we keep it in this format, and that just changes a little bit. But that's hidden, of course, on a higher level. But it's exposed on the user interface level. So I should say that the first author and the inventor of all this is Gianluca Frison, a postdoc in my team. And he is also an expert in assembly. Yeah, so it's basically C with hand-tailored assembly kernels. And they are tailored for different CPU architectures. And I should say that all this is open source with BSD2 license, so people can use, improve, and do whatever they want with it. And some industrial people use it, and sometimes they say, hey, we have another CPU. Couldn't you tailor BLASFEO for that CPU? And then Gianluca if they fund him for a while, he will make it possible. And the beauty of this is that we use, so to say, funding also from industry to produce a nice open source software that's useful for this company more than for others probably, but for everyone, because these things remain open source. So it exploits vectorizations. It supports also high-end and low-end CPUs. And as an extension, there is a compatibility with conventional BLAS API, which actually does, so to say, a part of this copy pasting of matrices. And it's still competitive. So that's at the core of most of our algorithms at the moment for embedded optimization. And this brings me to ArcADOS. So the principles of ArcADOS. So first of all, it's the successor of the Arcado toolkit, which we developed in Leuven and which used code generation also for the linear algebra. And that was, at the time, really extremely successful. We were very happy how fast actually the code generation of a lot of linear algebra loops could increase the speed. But the principles of ArcADOS are a little bit different, because this code generation also puts a burden on, let's say, debugging possibilities, extension possibilities, and so on. So ArcADOS should still stay efficient. That's obviously part of the game. But we try to get this efficiency by using, let's say, efficient low-level linear algebra routines, in particular BLAS-FEO. So that means the linear algebra will not be code-generated later on. It will just call BLAS-FEO. HPIPM is a solver based on BLAS-FEO, which is actually a QP solver, high-performance interior point method, also developed by Gianluca. And of course, it's using C, compiled language. It's relatively flexible, general, modular, and portable. So it's a self-contained C library with little dependencies, apart from, of course, BLAS-FEO, HPIPM, and so on. But these things are also self-contained C. So then there's the big thing in nonlinear optimization. You don't pass matrices to your solver, but you pass functions to your solver, right? And functions need to be efficiently executed. So you want to pass compiled functions to your solver. And actually, you also need derivatives. So you also need compiled functions and compiled derivatives functions to your software. And we, in the default implementation, ArcADOS uses Casadi for this purpose, and Casadi has this feature of code-generating the functions. But we only get from Casadi actually the model equations, so the continuous model, basically. Yeah? FC, you remember the one that we discretize later. And then all the discretization and of course, then the optimization is done in ArcADOS. So the problem is formulated in a relatively high-level interface, in particular from Python, MATLAB, Octave. You can work on it. You generate corresponding C code for the problem-specific solver. So you use only the ArcADOS C interface. So that's the ArcADOS itself is in C, but you can put formulate your problem in Python, and then it calls the C interface. And you can also generate S functions, for example, in Simulink. I should say we have solver interfaces for the NLPs, which have this OCP structure, and also QPs with that structure. And also there are particular interface, because sometimes it can be useful to have the ODE solvers that are used inside the embedded optimization to use them, for example, for simulation, or to implement an extended gamma filter or some things you want to sometimes call the integrators yourself. So you have also initial value problem integrators interfaced. And I should say that integrators are also part of Jonathan's main specialty. And Jonathan is now the chief developer of ArcADOS. So QP solver types and sparsity. Let's give a bit of an overview here. So we have roughly active set methods, interior point methods, and first order methods. So these are like out there in the MPC community, different solvers. They treat inequalities differently. Maybe for those that like ILQR or DDP, yeah. All this doesn't apply because you just say, I don't have inequalities, right? Then all are the same. But once you have inequalities, it makes a difference which QP method you use. And we currently favor actually either active set methods in a dense format or HPIPM, which is, okay, this is debatable if that's on the dense side. I think this is a sparse interior point method, but it exploits, okay, sorry, it's at the bottom. Okay, the OCP structure that we exploit is exploited in HPIPM. And HPIPM inside Arcados can also be called as a fully dense solver if you like. So I typically favor these options, dense QPoasis or OCP structured HPIPM. Maybe for the experts, we come to the dense problems by a procedure called condensing, which is like a sequential approach applied only to the QP. Yeah? So you don't destroy the good convergence behavior of simultaneous approaches by changing the linear algebra. And this is, so to say, just changing the linear algebra. Okay. I mentioned condensing already, and there is some form of partial condensing which was developed in the last 5 years, and which is somehow getting the best of both worlds. So you actually, nowadays, typically we partially condense, and then we use HPIPM as the QP solver. I mentioned already that Jonathan is expert on integration methods in Arcados in particular, and so Arcados supports different types of initial value problem formulations, ODEs, which we covered here in the course, but also differential algebraic equations. Of course, it is tailored to do fast sensitivity propagation. So you can call it from MATLAB, as I said already. You have different Butcher tables that you can get. There's an explicit Runge-Kutta method, for example, here, method number of stages 1, 2, 4. And implicit Runge-Kutta methods, so there's some, okay. Okay, now I get it, okay. Sorry, I didn't make this slide, but now I explain it basically. So the order of these the Gauss-Legendre methods is 2 times the number of stages. That's an interesting feature of them. So if you have, for example, method number of stages 2, then your order is already 4. Yeah, that's a method that we use a lot. Okay, and there is an implicit structure exploiting Runge-Kutta method that exploits some interesting system structure that we call generalized nonlinear static feedback. And to give it short, it's basically a slightly generalized form of a system class, which you should think of as the following. Imagine you have a nonlinear system, but it consists of something like a nonlinear linear input system that does something like filtering, integrating, whatever with your inputs. Yeah? Then it goes into the real nonlinear part, and then this nonlinear part outputs into a linear output system. Yeah? And then you would have basically some ways to leverage on this linearity of the input and the output system, reduce that. And actually the generalized form is slightly more general. And you boil, so to say, your Newton iteration inside the Runge-Kutta integration step. You boil it down to the absolute minimum of nonlinear operations here. So it's completely equivalent to iterating in the full space like we do with the like we explained it here, but you, so to say, look at every single step of the linear algebra operations in order to keep fixed what is linear. And then you basically exploit this fact that it's linear. So you can pre-compute a lot of things offline. And that brings me now to this, let's say, the part B of this talk, the third part, which is about a fast algorithm for closed loop robustified MPC. It's not about Arcados, but it's about, let's say, one of the more recent algorithms just accepted yesterday at CDC. And so it's basically latest research that I want to share with you. Before I record that, actually, I suggest we stop the recording for a moment and have time for questions.